so this is the topic. That's the topic. That is Oumuamua, which in Hawaiian means scout. And the reason that it's in Hawaiian is because the people who discovered it were on Hawaii. And this is not a picture of the actual object. This is somebody's idea of something that would be really cool that fits the description that the scientists gave it. So the description the scientists gave it was, it's 10 times longer than it is wide, although opinions differ, it could be 5, but they went with 10. And it's an interstellar traveler coming to Earth from outside of our solar system. This object came and went, visited us, and left. And it's the first one of its kind. Is this the only one? Is this object one of a class of objects, or is it, in fact, unique? Now, if it's one of a class of objects, okay, then the solar system has 100 trillion of these things whizzing through it all the time. 100 trillion of these things are coming by from time to time. And this is the first one we happen to see. However, now that's 100 trillion. However, that's if it's a class of object. If it's unique, then there's only one of them, and it's artificial. So you have your choice, 100 trillion or one, okay?
How long ago do they estimate?
How long ago what?
No.
Size.
Oh, I think 1,500 feet or 1,500 meters. Not teeny, by any means, but teeny enough that they were not able to take any pictures of it whatsoever. So there's no pictures of this. There's only the light curve that shows it dimming and brightening and dimming and brightening. But because of the way that it dimmed and brightened, for instance, if something is doing this, then it would do a certain kind of dimming and brightening. If it's doing this, it's doing another kind of dimming and brightening. In fact, it's not doing anything at all. It's not dimming nor brightening. And if it's doing this, it's doing a different kind of dimming and brightening. It was doing this. On the basis of that, they came up with that. Okay? But the light curve was simply nothing more than something doing this and this and this, like that.
They simulators who made a simulation of what it is that right? The they and that.
I wouldn't call that a simulation so much as an artist's conception.
Okay.
It's the artist's conception of what it is.
It is.
Yes.
Well, it's have to be artificial if it's not part of this class.
Well, you see, the thing is that you can imagine that this is a one-off event, but that's insane. We don't see one-off events. We see we see the one that we can see because it's near us, and then the ones that we can't see are further away. So yes, this is the nearest one to us, but it isn't, in fact. But it means that there's millions, trillions of them that are further away that we can't see. You just extrapolate from one.
100 years ago, we didn't have telescopes.
100 years ago, we didn't have telescopes.
That were good enough to see this kind.
Even 10 years ago, we didn't
Right,
have telescopes that were good enough to see this.
So did it enter our solar system?
So it entered our solar system. But by the time we saw it, it was leaving our solar system. So let me show you that.
Did they determine what it was made of?
Well, I'll tell you that. Did they determine what it was made of? Yes and no. So here it is entering our solar system. Here it is entering our solar system. and it goes inside the orbit of Mercury, and around this point we found it. How do we know that it went the way it did? Well, according to the laws of physics that were written down in 1600 and have not been altered one iota, not even by Einstein, because Einstein's theory of general relativity, which is all about gravity, has nothing to do with how you get from place to place in the universe, because basically all you need is Newton's laws. And Newton's laws tell you that there are three kinds of orbits, basically. Circles, which don't count because nothing's a circle. Ellipses, which is what this is, okay? And parabolas, which don't count, and hyperbolas. So really two kinds of orbits. Ellipses, hyperbolas, and as soon as you see a couple of points along the way, you can then extrapolate what the orbit is and you get a hyperbola. So even though they only saw it here and here and here, they were able to determine the entire orbit of the thing, determined that in fact it had passed close to the sun and had come from out there. They knew all that, even though they had never seen it along this path. So that's beautiful. What is it made of? Well, that's hard to tell because what am I made of? Okay, I seem to be wearing a nice shirt, and so I think I'm made of cloth. Okay, if you checked me out in a telescope, you would determine I was made of cloth. If you checked out this object that was coming from outer space, you would determine that it was made up of the stuff that's found between the stars. And you wouldn't know in any way what's inside of it. Okay? The only way you could know what's inside of it is if you got some other measurement that is not based upon light. Something that, because the light tells me it's sort of reddish, which is what the stuff between the stars is. That's why the surface of Titan looks red, because of the red stuff. When you take a lot of hydrocarbons and you cook them, they turn red. So everything in outer space is basically reddish. So you can't tell anything about what this thing's made of unless something else happens. And something else did happen. And that was this. Let's see. How am I best describe it? Okay. So something that's the sun, and something that is going away from the sun in that direction. Gravity goes down like this. And I'm sorry, I'm going to use a number here. It's 1 over r squared. Meaning, the further you go away, the bigger the r becomes, and the smaller the gravity. I'm going to say gravity. Gravity equals something 1 over r squared. So the further you go away from something, the smaller the gravity. Means and because the gravity is less, the thing slows down less. When it's leaving close to the sun, it's slowing down a lot because the gravity is pulling on it hard. When it gets further from the sun, gravity is not pulling as hard, it doesn't slow down as much. Okay? So this is what you take some data and you fit it to this law of physics invented by Newton. This is Newton's law of gravity. You'd like to see the whole thing. It's called Newton's law of gravity. In its entirety is force equals big G, big M, small m. That's Newton's law of gravity. That's the entire thing. That's it. That tells you everything you need to know about how things travel in outer space.
As someone who was tracked out of math way too early, why the symbol R?
For radius.
Radius. That's what I figured. But
Yes,
I
radius.
Before I stuck my neck out there. Radius. Gotcha.
Okay.
Gotcha.
Yes.
Is it moving the same speed as most comets do?
Comets move slower This one is moving faster. The reason is that
Quiet.
I thought I could hit him with this. So the thing is, that's the law of physics. So that tells you how the orbit goes. So if anything, if the orbit doesn't go like this, if there's something else going on here that makes the spacecraft do differently than it shows up in this animation, then you have to ask the question, what's going on here? Well, the fact is the data showed that it wasn't doing the hyperbola thing. It was doing something else. And that's against the laws of nature. Unless, of course, it's not obeying the laws of nature. Unless it's obeying some other law. Like maybe there's something artificial about it. Artificial. So since the last class, there has been a conversation that has taken place in the media and on the networks and throughout the world about some guy who said that maybe this is an artificial spacecraft. The guy is the head of astronomy at Harvard University.
Okay.
Okay?
Got a good credential.
He's got good credentials. Right. So this brings up a topic that we should discuss, is given the unlikely, see, at this point you know very little about the whole story. I haven't told you the whole story. I will tell you the whole story. But background, think about this. You have the credentials to say something about this, okay? You have data that tells you that something is funny and needs to be explained. You have that data. The data is real. This is not behaving properly, okay? And you decide to go with the most unlikely explanation you can possibly imagine and get your name into the papers,
Right.
okay? And this is going to go worldwide viral. Everybody's going to be talking about it. And as Carl Sagan once said, extraordinary claims require extraordinary evidence. The thing is, it's an extraordinary claim, but the evidence, which is the small small deviation from a hyperbolic orbit, is not an extraordinary evidence. There's something other than going on. What could possibly be? Well, there are actually objects that misbehave in the solar system all the time, and that are not artificial. And what are they? Well, you can have a comet. Have you ever seen comets have a tail? Comets have a tail. That tail is like a rocket motor. There is stuff being thrown off the comet. The comet's spewing stuff out its rear end, and as a result, it's got a rocket motor which is pushing it in any way it likes to go, but not necessarily according to the laws of nature. It's according to the laws of what the comet feels like at any given moment. So the comets do this sort of abnormal stunt all the time. So maybe it's a comet. That's the answer. Maybe it's a comet. But no. Turns out people have thought about that. And they measured it, and they were really careful to make sure. And it's not a comet. It's not behaving like a comet. There's nothing sticking out. There's nothing blowing out its rear end. But that would have been a good explanation. And the other explanations that they come up with are also no good. So there aren't any good explanations for this. There really aren't any good explanations for it. And worse than that, this thing is never coming back. It's never coming back.
What do you call it?
Oumuamua. Oumuamua meaning scout in Hawaiian.
Means what?
What is it called? That's what it's called.
If it comes from outer space, could they have different rules of physics?
If it comes from outer space, could they have different rules of physics? Now that is a good question.
Right, lady.
And believe me, that is you're not the first to have asked that question. However, and you're not going to be the last person to ask that question. And there have been teams, hundreds of people, for hundreds of years answering that question. And to the best of our knowledge, the answer is the rules, the laws of nature are the same everywhere you look. Now, if you, and point to one of the people in our class, Elaine. Elaine happens to be a person who has bigger thoughts than most people who study astronomy. She's looking at other universes. And when it comes to other universes, that's when the question becomes relevant. Because we don't know if the laws of physics in other universes are the same or different. And if you ask the average astronomer, who will tell you without a doubt that the laws of physics here and there are exactly the same, if you ask that same astronomer the question, are the laws of physics the same everywhere? He'll say yes for here. For other universes, he will just as easily say no. The laws of physics in other universes are probably different. So that's the answer to your question. But for this universe, we think it's the same.
So how would you get from one universe?
How would you get from one universe to another? Right.
Well,
I don't know. I mean, really, see, there are things that are beyond our capabilities. I mean, you could say present-day capabilities, and you'd be right. But people have, in fact, asked that question about this thing. Okay, they have said, okay, we only get one shot at this thing. It's already passed into the solar system. How would we, if we thought that we really needed to see this thing? Let's say we really thought it was artificial. Let's say, for example, that when they pointed their radio telescopes to it, to the FM band, put on their earphones, they heard music,
yeah.
right?
Gotcha.
Or alien garbled stuff. Which they actually did do. I mean, this thing went crazy. Everybody did everything they could possibly do to check out whether this thing was in fact artificial, because it was in fact unexplained, and is still in fact unexplained except for one explanation, which the head of Harvard University put forth, which is that it's artificial. Okay.
What's his name, by the way?
His name is Avi Loeb, and he's from Israel. Yes.
He who defines
have
his...
correspondence from Harvard University.
You have.
Well, they do.
They have. Yeah.
With Galileo.
They have. Harvard
Back
has.
and forth with Galileo.
Harvard has correspondence with Galileo.
Yeah.
Okay. And
It was founded in 1630.
1630, right? So they were talking to Galileo,
Yeah.
right? And now they're talking to this idiot. But I'm sorry, I don't want to.
In 1630? Well, never mind. We'll let it
Anyway,
go.
so
I don't think so.
Who was
Harvard-
talking to Gal?
Harvard was, you know, it's too
Harvard
soon.
faculty members.
Well, I lost my train of thought. So he's proposing that be artificial. I'm losing my train of thought here. So if it was artificial, if they did hear "I Love Lucy" coming back, or they heard anything coming from it, then the people who wrote this paper that I read asked the question: is it within the capability of our civilization to reach that comet or that object, given that it's where you see it is? It's already leaving our solar system. It's leaving at 21 miles per second. Can we catch up to it? And the answer is, of course we can catch up to it. How much would it cost? and so depending on how soon we start the project, okay, it'll cost $100 billion, $200 billion, $1 trillion. The longer you wait to catch up to this thing, the bigger the rocket has to be, the faster it has to fly, and you don't want to just fly to it. You also want to it to slow down as well, because you want to, if it's an alien spacecraft, you certainly don't want to fly by it. You want to fly by it and then slow down and then land on it. So you want to do the whole thing, yes.
Do they even estimate how fast it went once it left our solar
It's not an estimate, they know exactly.
How fast did it go?
What would be meaningful to you? How fast did it go? The things in the outer space go at miles per second, okay? The Earth, astronauts going around the Earth, go around like, and I don't remember the numbers actually, but I'm saying, let's go with 7 miles per second, okay? Let's say that. 7 miles per second. Could be 11, I'm not sure. If you want to escape Earth's gravity, maybe 21 miles per second. Okay? If you want to escape the solar system entirely, maybe 30 miles per second. How fast is the Earth going around the sun? Maybe 20 miles a second. Those are the kinds of numbers, and they're not necessarily right. So this guy is going at maybe between 20 and 40 miles per second, probably 20 miles per second. And that's what you got to do to catch up to it. But you have to get there before it gets further away, so you have to go faster than it. So you have to go faster than anything has ever been sent anywhere before. And you can't use see, when you want to go faster to save money, what you do is you take yourself and give yourself some gravitational assists by going past Venus and Jupiter and Mars, and so you swing by here and you swing by here and you swing by there, and you get all these extra propulsions. But of course it takes you 7, 8 years to get the extra speed. We don't have the time, so if you're going to build a spacecraft, better go on a direct route, find it, land on it, take a look what it's about. That ain't going to happen. Because there's no evidence aside from this guy's idea, and I'll tell you, I still haven't told you what the idea is, why it's artificial. What's the question?
Could it come back?
Could it come back? The word hyperbola, by its very nature, means it comes from infinity and goes to infinity. That is the definition of hyperbola. So no, it can't come back.
And other galaxies have exactly the same laws of physics.
And every galaxy, well, first of all, every galaxy has the same laws of physics. Now, remember, we are talking scale-wise, we're talking about their nearby stars. Okay, if you were building a sandcastle in the beach and you're using a thimble, the thimble would represent the nearby stars around us, and the stars and the beach that you're sitting on is the galaxy, and you're asking about grains of sand on other beaches. So the laws of physics are the same in the thimble, on the beach, on other beaches. Those are other galaxies. The laws of physics have been determined to be the same in other galaxies. Mm-hmm. As far out as we can see, we see the laws of physics behaving the same. How do you do that, by the way? It's very simple. You look at the light, you know how the light is made. You know the light is being made by, this is an atom, this is an electron. I will draw it in the way that you learned when you were in high school. And this is an electron going around in a different orbit, okay? Mm-hmm. And electrons will jump from one orbit to another orbit, and as they do this, they lose energy and they emit a ray of light. Mm-hmm. That ray of light has a particular frequency based upon the fact that this is an atomic nucleus of a certain weight, this is an electron of a certain size, charge, and everything. So the ray of light that comes from that atom has a frequency that it only could get if it came from that atom. So when you measure that frequency, you say it came from that atom with this proton and that electron, and that's why I know that protons and electrons and galaxies on the other side of the universe have the same characteristics as the atoms on this side of the universe, because I can measure the frequency of the ray of light and tell you it's the same frequency, so I'm not in any kind of mystery. I know exactly what's going on the other side of the
You
universe.
said a ray of light, I mean, it's a photon, isn't it?
It's a photon.
Okay,
Right, it's a photon.
okay,
So I can really tell if the things are the same or different.
okay.
They have, and that's just one example of being able to know the laws of physics someplace else. There are there are more complicated questions that have more complicated answers, and there are some questions that don't have answers. To the extent that we know answers, we know the laws of physics are the same. Yes.
Does a baseball hit involve going in the air and roughly follow the rules of a hyperbola?
If a baseball is hit, does it roughly follow the rules of a hyperbola? And no, it doesn't. It roughly follows the rules of a parabola. A parabola. A parabola is the arc that a baseball takes when it is thrown. A parabola. Not an ellipse, a parabola. It's interesting. Why is it a parabola? But in the Earth's atmosphere, it's also governed by friction in the atmosphere, so it doesn't go quite that well. Yes.
There's a saying, he who defines is master of the universe. Now, that's just for words.
He
Okay,
who defines
is
is master of the universe.
Don't ask me exactly.
I know
but
what
it's
that means.
It's very, so he, in effect,
He is who?
He is Avi, whatever his
Avi,
name
okay.
was. What, if anything, is his, not evidence, but at least
Okay,
his
so
theory?
now
What is
you
he saying?
okay. So I have given you no reason whatsoever to explain why he thinks that.
Right.
Okay?
Right.
And I managed to get through half an hour of this lecture without anyone asking that question. So,
You said you're
I'm going to ask it, now I'm going
Okay,
to
yeah,
answer it.
no, I'll let you continue.
No,
but I'm just
I know.
curious what the-
It's just we didn't seem to get to the
It's
end.
just, you said
Have to
because
get
of his
there. Have to
position.
get there. This
Because
is-
of his position, he can
Okay.
do it.
No. It's not just
But he has
because
to have
he's position.
something.
He has something. He has
to-
something.
He has to
Okay?
have something. Okay.
Okay. So the thing is that the object is moving. The gas is coming out of a comet isn't doing it, but the sun could be doing something to it. The sun emits photons. The photons are not gravity. They travel at the speed of light. And if you were being hit by a photon, as you are right now, you would be pushed backwards by the photons that are hitting your body at any given time, except the photons have incredibly little ability to push you backwards. But they do have something that is called momentum. They have momentum. Just like if I threw this at you, I'd hit you and it would hurt you because it would hit you and push your stomach in. This has momentum when thrown. Light has momentum when it hits your body, when it hits any object. So perhaps the light that's coming from the sun has enough momentum to push this object so something else besides gravity is affecting it. Perhaps it's the pressure of the sunlight known as radiation pressure. Perhaps radiation pressure, it's not gloriful, but it's impossible. Radiation pressure isn't that much pressure because it's the thing which you saw earlier is big and it's probably made of rock and stone, and the radiation pressure can't do anything to that big massive piece of rock unless it's not a big massive piece of rock, unless it's incredibly just the opposite, unless it is as thin and as unmassive as possibly it could be. And in fact, maybe it's big and thin, and maybe if you look at it sideways, you can't even see it because it's so thin, but when it turns to its face towards the sun, it's thick. And maybe a thin, very light object can be affected by the pressure of sunlight. That's what he said it was. He said it was a thin object. It wasn't just him, he had a co-author. He said it was a thin object being pushed by the sun. And how do you make a thin object? Well, you manufacture it. An alien civilization would manufacture it. So that's how come, and he figured out what it'd have to be. He figured out exactly what the dimensions of this object would be. They're not unusual. About a millimeter thick, about this big, or maybe, bigger, like, a mile big, but thin as a sheet of paper, even thinner, and a mile wide, or less than a mile wide. And it works. It works. The thing slows down the way speeds it up and slows down the way it was supposed to. So he was right. If in the sense of he had a theory that works. And he has the only theory that works. Therefore, he gets to raise his hand and it says, excuse me, and he's head of Harvard, excuse me, I have this idea, it's really not likely, but, explore all possibilities. And he did. He said, would it make it from the Earth, from outer space, stars far away, could it get here if it was made of this very thin material? So we actually studied whether or not this tumbling object would be able to survive for millions of years in space. And he came up with the answer, yes, it does work. And will it be torn apart by tidal friction? No, it will work. And will it survive being penetrated by all sorts of things that are flitting through the cosmos? Because there are all sorts of things that are flitting through the cosmos at microscopic scales. Will it survive that? Yes, it could. And he said, you know what? I just figured out that you could engineer this thing and it could work. I did it. I figured it out. It works. And by the way, you could use my calculations to create a starship of your own. Okay? Now that's interesting because it turns out that Avi Loeb is on the team of creating a starship of the very same ilk. Avi Loeb has created something called actually, I keep forgetting the name, so I'm going to, yes. He has created something called, he has joined a team of other people, including Stephen Hawking and Mark Zuckerberg, okay, to create a project which was funded at the rate of about $100 million by a Russian oligarch. We have $100 million so that a project could be started so that we could use this same technology that is being used by this Oumuamua to get to the nearest star. It's called Breakthough Starshot. It's called Breakthough Starshot. He's on the board of directors. And would you like to see how it works? Okay. There's no sound in this. Okay, so a satellite is launched. The satellite is launched. If you notice, the satellite is shaped like a square. It is the shape of a solar sail. We have on our planet, in this last decade, we have built and tested solar sails. These were science fiction 10 years ago. They exist. In the present day, solar sails are real. We have launched them. We would launch this solar sail, thousands of them. The solar sail is big and very light. This array of telescopes built in the desert, 1 mile in diameter, using more energy than 100 nuclear plants, is about to fire a laser at that solar sail. They're pointing it at the solar sail. The solar sail better not absorb the light, because if it did, it would melt. Okay? It's 100 gigawatts is being sent to this poor little itty bitty thing. And within a short period of time of minutes, this thing is going to be accelerated from standing still to 20% of the speed of light within minutes. And it's on its way to Alpha Centauri. And they're going to do this 1,000 times over. This is the next one. The next one is being sent, and the next one is being sent. And the cost of this project is only, present day dollars, about $100 billion. Who knows? It could be cheaper. It has to fly through interstellar space. It has to not break apart as it's hitting things. It has to have a camera. It has to have, there's Alpha Centauri. There's the planet that it wants to take a picture of. It's taking a picture of that planet as it passes by. This planet looks like has oceans. Takes a picture of the planet. There's the picture it took of the planet. And now it took it with these little cameras on board. It has a little nuclear source. It's going to now send back the picture from 4 light years away. It's going to send the picture back. The picture is going to pass all the way back to Earth and be received by Earth. And in that array is going to pick up the signal from 4 light years away, and we're going to find out what the planet circling the nearest star looks like, okay? And this is funded at the rate of $100 million. They need $100 billion, okay? But it's real. And so if Ari Loeb says something crazy like maybe somebody else is doing it, it's not so crazy. It's less than crazy. Breakthough Starshot.
These people are the new Isabellas, of our time. These very rich people who are funding this stuff. I kept, Ferdinand and Isabella of our time.
They are Ferdinand and Isabella of our time.
Right.
That's a very good analogy.
Yeah.
Because Columbus wouldn't have come here unless somebody thought that was a good idea, funded him, okay? And in this day and age, all these very rich people are taking their large amounts of money and putting it towards some goals that are completely outrageous. And one of these goals could someday come to fruition. Next week I'll tell you about another crazy goal that Elon Musk is doing that will happen within half a decade. Within your lifetime, Elon Musk will have done something that's very crazy and very real because he has the money and the vision. But I won't tell you what it is. Let me see if there's anything else.
The car wasn't crazy enough. No, I'm kidding. That was fun.
Right. So I'll play this video because I'll tell you this one. Okay. So Oumuamua has a trajectory. The trajectory, you can figure it backwards to figure out where it came from. You can literally say, "Oh, I see. Over there. Okay. Yeah, it came from over there. There's nothing over there, right? Oh, yeah, there's something there now. But you know what? It wasn't there when Oumuamua was there. What was there when Oumuamua was doing its thing? So let's reconstruct what was near Oumuamua during the time that Oumuamua was traveling. There is a survey that was done recently. Unbelievable unbelievable survey. They have over 1 billion stars that they know exactly where they are in the sky and which way they're going. And so they know what the sky was doing now, and they know what the sky was doing last week, last year, and 1 million years ago, 10 million years ago. They know what the sky looked like. They can reconstruct the path of Oumuamua through the stars that it passed by years before. And the sad thing is there were no nearby stars. The nearest nearby star was 2 light years away. And it was 138 million years ago that it was near that star. Nevertheless, 2 light years, 138 million years ago. I wanted to show you just, if I have it still going on, because I put it up. This is the solar system, and let me just block my own. This is the solar system, and I'm going to go out to where approximately Oumuamua came from. So that's the planets, orbits of the planets. That's that's that disk of debris around our sun. We're now at 10 light years. We're now at 100 light years, and I'm stopping. These are the nearby stars. These are the stars that are near our sun. These are the actual stars that are near our sun. And Oumuamua came from one of those. Probably one of the actual stars in this simulation is where Oumuamua came from. But the thing that strikes me about it is space is empty. Space is really empty. And millions of years have to go by before something from there gets to here. Nevertheless, it looks like space is crowded, but space is unbelievably empty. Yet, if it isn't artificial, if it is real, and just come from one of these stars as being things that were formed at the same time that these stars were formed, then the truth is space is filled with Oumuamuas. The space that I'm showing you, which contains hundreds of stars, is filled with hundreds of trillions of objects the size of Oumuamua, and hundreds and hundreds of trillions of things that are much smaller. So that's the story. I'm going to now play a video of somebody who's going to explain what I explained again, but she's nice and interesting, and we'll end the lecture with that.
You're nice
Let's
too.
get this straight. A bunch of scientists, including Stephen Hawking, want to send a tiny spacecraft to the next closest star using a giant laser. Russian billionaire Yuri Milner has already invested $100 million into the project called Starshot to see if this type of technology can actually work. So let's break this idea down a bit. It's known as laser propulsion and works exactly how it sounds. A laser beam is used to propel a vehicle very rapidly through space. It's kind of like using a hose to push a ball forward. The laser's light carries momentum just like the water from the hose, though it's nowhere near as powerful. But if you have a big enough laser and a small enough spacecraft, you can potentially transmit enough force to the probe so that it moves very, very fast. That's what Hawking and Milner want to do. The idea is to create a tiny wafer-sized spacecraft connected to a reflective sail that stretches a few meters wide but is only a few atoms thick. It's kind of like the Planetary Society's solar sail concept, which uses the sun's light to move through space. The wafer is also meant to hold a number of miniaturized instruments, including a power supply, cameras, and a communication system. Once the spacecraft is positioned in orbit, then it's time to turn on the laser, or actually lasers. First, that involves building an array of laser amplifiers on Earth that take up about 1 square kilometer. One laser is fed into these amplifiers, which break the light apart into thousands of beams. The directions of those beams can be adjusted to form one giant beam of light that travels up out of Earth's atmosphere and hits the spacecraft's sail. The lasers will be turned on for about 3 to 5 minutes, sending the probe through space at 1/5 the speed of light. At that pace, the spacecraft should get to Alpha Centauri in a mere 20 years. That may seem like a long time, but you have to remember that Alpha Centauri is 4 light years away. That's 25 trillion miles. For comparison, NASA's Voyager 1 spacecraft has been traveling to Alpha Centauri at 40,000 miles per hour since 1977, and it's only 0.005% of the way there. Starshot sounds really cool, but there's still a lot of work to be done before this idea can become a reality. The array of lasers needed for propulsion has never been built before, and scientists still need to figure out how to miniaturize all the instruments on board the spacecraft. That includes miniaturizing a communication system that can span 4 light years of space. The sail also poses an engineering challenge. It needs to be made extra robust so that it can withstand the intense accelerations through space, and it must be as reflective as possible. If it absorbs too much laser light, the sail can melt. Additionally, the path between Earth and Alpha Centauri isn't exactly empty. The chances of hitting something big like an asteroid are small, but lots of interstellar dust still stands in the way. And with the spacecraft moving at 1/5 the speed of light, hitting just a tiny speck of dust will pack a big punch. Engineers will have to build a redundancy system for the sail so that it can withstand a few high-speed dust collisions along the way. And of course, there's always money to consider. The $100 million from Yuri Milner will help jumpstart some of the research and development needed to prove this technology actually works. But a project like this is comparable to CERN or the Apollo program. It's going to need billions of dollars to succeed. That means it could be many years before we see this spacecraft even start its journey to Alpha Centauri. Interested in a much slower form of space transport?
So science fiction
Yeah.
in your lifetime,
Yeah.
or at least in your children's lifetime.